Conservation of matter. I often hear people reciting the law of conservation of mass, probably because they learned it in school. I also hear recitations of the conservation of energy. Yes, I learned that in school too. But things have moved on since school physics. Now we call that classical physics, and it's a good approximation in most circumstances, but not always. First of all, let me make the point that mass and energy are really the same thing, linked by that well-known equation E equals mc squared. This was discovered by Einstein and is a consequence of special relativity. So a better question to consider is the conservation of mass energy. In classical physics, that conservation law is absolute, but not in modern physics. The key thing to think about is Heisenberg's uncertainty principle. As everybody knows, if you know the position of a particle, then you don't know the velocity. So, put a particle into a box at rest. Because it's in a box, you can know that there are limits to its position. But that means that a moment after you insert the particle, you don't know its velocity, which means that you don't know its kinetic energy, which means that the kinetic energy is no longer zero. The same uncertainty principle that applies to position momentum also applies to time energy. The conservation of mass energy is not true at the quantum level. This sounds counterintuitive. How can you get something from nothing? But the whole of quantum theory is counterintuitive. Why should our intuition, which rests on our personal experience, be relevant for how light and subatomic particles behave? Special relativity itself is not intuitive. That's why no one thought of it until 1905. Quantum mechanics is deeply non-intuitive. Richard Feynman said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." So, can we test this idea? Yes, we can. Suppose we have two metal plates without electric charge and close together. Because subatomic particles pop into and out of existence between them, that would lead to a force between them, pushing them together. And that force has now been measured. This is called the Casimir effect. Casimir with a K. You can learn more about it, if you like, by Googling Casimir effect. So now we know that these quantum vacuum fluctuations are real and have been measured. This is a real-world example that shows that conservation of mass energy is not true, and you can get something from nothing. The reason you might think that you can never get something from nothing is your own intuition and personal experience. But quantum theory violates intuition and our experience big time. So, would it be possible for a quantum vacuum fluctuation to be large enough to generate an entire universe? It's very, very unlikely that this would happen. Very, very, very unlikely. But not impossible. And one of the things that we know from quantum theory is that if something is actually possible, then given a long enough period of time, it will happen. Thanks for watching this video. If you would like to discuss this with me, you'll find me on Facebook in the Religion Discussion Group. See you there.